Hi, this is Steve and welcome to our video series. In this segment we want to look at lower heating loads, modulation, and their effect on efficiency. So let's set the table. Houston, we have a problem. So let's look at the heating season and the heating loads. This isn't a new issue, but it's becoming more and more important because of the increasing expectations for comfort, because of the cost of energy, and because of the environmental concerns. We want to make sure the equipment's running efficiently all the time. So in heating season, again in summer, so this is an inverted heating season where the temperatures are down. So we see mid-January being our coldest month. But here, as we come out of summer, gradually the temperature is going to get colder and colder. We don't need a lot of heating in late August or September even. Once we get into October, you might need a little more, and then as we go into December and January, obviously we peak at our heating load, and then once we come into spring, then we start to decrease again, and as we go into May and June, we don't need any heating again. So we start kind of at zero heating need, and then increase our heating demand, increasing heating demand till we peak, and then can follow it down. So let's look at an example. So here I've pulled out data from actual Toronto. So this is Toronto's average winter temperature. And again, you see it's an inverted curve where we have Celsius and Fahrenheit going down. So we're going from 20 to 10 to minus 10, or on the Fahrenheit scale, 68 to 50 down to 14 degrees Fahrenheit. And then we have January. So we have August, September, October on the top. So the months on the top, the temperature. So we see as we go into the winter months, we get colder and colder and the demand goes up. So let's assume we have a 60,000 BTU furnace, one of the #1 selling furnace sizes in North America. And let's see what that means. So first we determine our heating season. So we look at, let's say, temperatures. Anything where my maximum daily temperature, so this is my minimum and maximum, and the average temperature in the dark red line, but the pink lines bound the maximum and minimum for the day. So when my maximum temperature for the day is below 65, and 65 would be about 18 degrees Celsius, then we know we're going to need a little bit of heating. So that's where we would start, and that's in Toronto, kind of at the end of September, first week in October. And that will run all the way through till middle of May. And once we hit the middle of May in Toronto, then we won't need any heating any longer. We get into the summer temperatures. So that's our heating season. This would be our peak day. So this is January, and we're looking at an outdoor temperature of maybe -8 Celsius as our design load. So again, as I mentioned, anything above that kind of 65 degrees, we don't need any heating, so that'll be the baseline. So this is where we need no heating. On the other side of that, we have maximum heating, which is our coldest day in January, where we need maximum. In between there, we don't need maximum at all, but we need more than minimum. We need more than zero. So let's look. Well, okay, because each of these are categorized in 5 degrees Celsius increments, it kind of makes it easy. The line's fairly linear, so we can divide that up evenly. So in this section, we need, let's say, approximately 50,000 BTUs, and that would be December and in February, and then 40,000 BTUs, and then 30,000 BTUs, 20,000 BTUs, and then 10,000 BTUs. So these are kind of the amount of heating we need at each section of the winter. Yeah? As we take these 4, 5, 6 months and divide them up. So what it shows is that, so at the end of September, I'll need about 20,000 BTUs. If I'm in November, I'm going to need about 30,000 BTUs. Okay, so that's our curve. The point of this is that the maximum heating load is in the middle of January, but the rest of the season doesn't need anywhere near 60,000 BTUs, and we should have equipment that is able to operate efficiently regardless of where we are. And again, this isn't new. We've had we know that every year coming out of summer, we won't need any heat, but then as we get into September and October, November, we will gradually need more and more. But again, it hasn't really been an issue because gas has been cheap, environmental concerns weren't really that big an issue in the 70s, 80s, 90s, so we had equipment that did not, put in a furnace, oversize it so that they'll never run out of heat and it'll be fine. That's not what we want to do these days. So some challenges. First, heating loads are decreasing. We've got improved building technology, so our windows are getting better, our doors are getting better, our insulation is getting better, right? If you look at we're foaming up a lot of the houses now, so they're airtight. The exterior envelopes are getting better. All of that leads to much lower heating loads, Cooling loads are increasing. Sorry, I don't know what that was. Cooling loads are increasing, so even with better window technology, seems we're putting in more window square footage. So our window to wall ratio is actually increasing. So our cooling loads are actually going up, but our heating loads are going way down. So what does that mean? Well, our heating and cooling equipment needs to be able to work efficiently, again, not only at the maximum, but also at the minimum throughout the heating season. But unfortunately, our single stage or two stage furnaces and air conditioning systems are not able to deal with those smaller loads, both on the heating and the cooling side, so we need some better equipment. So that's unfortunately what the industry needs to do, and we as manufacturers need to address, right? Minimum inputs need to be lower on our equipment. And then our turn down ratios, or the ratio of maximum to minimum, or the width, or the range of the staging, or the modulation, or the range of the variable speed needs to be closer to zero on the heating side, because as we know in September and October, we just need a little bit of heat. We don't need anywhere near maximum. And the same on the cooling side. I might need a little bit of cooling in the afternoon with the hot sun, but I don't need cooling the rest of the day. So I need to be able to deliver just a little bit of cooling would be ideal. So both on the heating and the cooling equipment, it's the same issue, just inverted. We need to be able to deal with whole home loads and partial loads both efficiently and comfortably. And you can imagine if your heating equipment is cycling on and off, the temperature in your home is going up and down as well. So there's a comfort factor as well to the efficiency. We can't always be cycling the equipment on those micro loads. If we don't address it, then the cycling will continue, the poor performance will result, and the temperature swings will continue to be the norm, unfortunately. So let's look at some of those heating loads that I mentioned. Well, Natural Resources Canada has included this in their design guide. So what they did is they looked at a 1,400 square foot home. They looked at that home in 4 different areas, 4 different cities, and they designed it to 3 different building codes. Standard building code, Energy Star for new home building code, which is 20% better than our standard building code, and then R2000, or let's say our net zero, which is kind of the premium efficiency design. And again, they looked at it for 4 different locations. But let's just take Toronto for example. So a 1,400 square foot single family home, detached, in Toronto, on basic standard construction, heat load under 20,000 BTUs, right? 19,000 BTUs. If we build it to Energy Star for new homes, again 20% better than standard, now we're 16,000 BTUs. That's the that's the heat load in the middle of January. That's not your heat load in September, October, November. That's the heat load in middle of January. And then we have R2000, even lower, so we're down to about 12,000 BTUs. So that was for Canada. Now let's look at the States. Similar situation. Here we have 5 different homes, or 5 different locations, and we've modeled 1,600 square foot homes in these. And again, when I say we, GTI has modeled the performance. So we have 1,600 square foot homes using a 60,000 B2 furnace in these 3 or 5 different areas. 2 are in quite cold areas, right? Blue is Madison, Wisconsin, so they've got a fairly significant winter. We have Albany, New York, again, as you see, significant winter. Then we have Portland. Portland would be representative of the Northwest, so you're looking at Seattle, Portland, Oregon, and Vancouver, would be representative on that curve. And then we have LA and Birmingham. So you see LA in the yellow. It also has a curve, but because it's a warmer area, the curve is going to be this way. So it still has that curve function, the same as all of these have the curve, same as the Portland has the curve. It's just swung a little bit more to the left. So warmer areas will be swung to the left, cold areas more to the right. Again, needing more BTUs, needing less BTUs. But all to say that most, when we look at all 5 of those areas, you see that most of the heating distribution, even in the cold areas like Madison and Albany, is still in this range. So we're looking at 3,000 BTUs to 24 or 30,000 BTUs, somewhere in that range, 5% to about 50% of the 60,000 BTU furnace. If we average those 10, well actually now we're going to add a few more homes. So we had that one distribution, now we're going to add these 10 locations, 5 of them being very cold weather areas that have significant winters, being Bozeman, Montana, Bismarck, North Dakota, Madison, Wisconsin, Chicago, Illinois, Albany, and then for moderate, we're looking at Portland, Nashville, Birmingham, Austin, and LA. So all to say that we're taking these 10 cities, we're averaging them out. 5 of them are cold weather, 5 of them are moderate, and putting them all together to see what type of distribution we get, if we can see something that's representative of all of, let's say, the US. What we find is when we average those 5 out, again for a 1,600 square foot home, this is where our distribution comes in. So if we look between the dotted lines, 3,000 BTUs to 30,000 BTUs is where the majority of the demand is. And that's 5,000 or 5% to 50% of a furnace of 60,000 BTU furnace. So we know that it has to operate well from that 5 to 50% range, because that's where most of the heating is going to be. So again, if it's a warmer area, this bell curve will just swing to the left. If it's a colder area, this bell curve will just swing to the right a little bit. If it's a smaller home, it's going to need less BTUs, similar, swing to the left. If it's a larger home, it's going to swing to the right, representing more BTUs because it's a larger home. So, but all to say that the curve will be very similar in terms of its distribution. So, modulation. So what is modulation? Modulation, I often use the car reference to kind of explain modulation. When you push the accelerator on your car, RPMs come up and your engine will react and your car will move faster. Take your foot off the accelerator, it slows down. But you can go, just by pushing the accelerator and bringing your foot off the accelerator, you can adjust how fast you go to whatever speed you need. If you're in traffic, you want to slow rate down to maybe 20, 15 miles an hour. If you're on the highway, you can go 60 miles an hour. You can go anywhere in between there. You can go 37 miles an hour, you can go 55 miles an hour, as you need depending on the traffic. Your furnace, again, we looked at the heating curve, your furnace should also be able to do that. It should be able, when you need 23,000 BTUs, it should be able to deliver 23,000 BTUs. When you need 48,000 BTUs, it should be able to deliver 48. When it needs to go to maximum, it should be able to go to maximum. Unfortunately, that's not the way it is. Here we have the different furnaces, and I've kind of used that speedometer because we're going to compare 60,000 to 60,000. On a single stage furnace, it can only operate at one speed, and that's maximum. right? So if we compare it to the car, it's like driving at one speed. I can drive at 60 miles an hour, or I'll be off. So that's not going to be able to drive at any other speed that we need in heating season. It won't be able to deliver at, 20% or 50% or 70%, right? It's 100% on or off. A two-stage furnace gives you two speeds. So it'll run at maximum, 60,000 BTUs, or at one more speed, which is usually between 70% and 50%. So in this case, if it's a 60,000 BTU furnace, it'll operate at 60,000 BTUs or 30,000 BTUs. It's not going to run at 10, it's not going to run at 20, it's not going to run at 30,000 BTUs, it's going to run at, or 25,000, it's going to run at 30,000 BTUs or 60,000 BTUs. When we get into modulating or condensing, or modulating furnaces, then we can have different ranges. So this is a 5-to-1. So we have 100%, 80%, 40, 60, 40, and 20. So we can run at 5 different speeds, which is much better operation than the two-stage or the single-stage, but we can do even better. If we look at a lot of the boilers, we're operating at 10-to-1, which means we can operate at 10 different speeds. So all to say here, the more speeds that your equipment, heating and cooling, can run at, the more precisely it's going to be able to match that heating and cooling curve and also deliver comfortably into your home, right, without cycling on and off. So this is kind of a quick idea of what modulation is. It's referring to the speeds of your equipment, the number of stages it can operate at. And we have what we call a turn down ratio, and the turn down ratio is the maximum input divided by the minimum. So if I have a 60,000 BTU furnace with a minimum input of 30,000 BTUs, 60 divided by 30,000 is 2-to-1. So that would be a 2-to-1 ratio on a furnace that has a 30,000 BTU input. So now let's look at some actual equipment and we'll put that into use. So again, we're going to stick with the 60,000 BTU format. Again, one of the top 2, if not the top furnace size in North America, so we'll stick with that. So we've got a maximum input of 60,000 BTUs for all the equipment on the heating side. Now we're going to look at the minimum input, and then we're going to calculate the turn down ratio. So a single stage furnace so a single stage, again, operating at one speed. 60,000 is the maximum input, 60,000 is the minimum, so a turn down ratio of 1-to-1. Two-stage furnace with stage 1 at 70%. Again, maximum is 60, minimum 42,000 BTUs. Turn down ratio of 1.4-to-1. Two-stage furnace with stage 1 at 50% of maximum. So we have 60,000 as our maximum, 30,000 as our stage 1 at 50%, giving us a turn down ratio of 2-to-1. And we have a variable speed modulating furnace, again 60,000 BTU, with our minimum input of 24,000 or 40%. That gives us a turn down ratio of 2.5-to-1. This is one of the better furnaces in the market, Energy Star rated, top AFUE, and that it can modulate down to 24,000 BTUs. So when we think about our curve again, when we need that very low BTUs in September, October, and again in April, we have to look at this minimum input and see how does that relate to our lowest load. So then let's look at tankless options. Again, on the iFLOW side, we're looking at combination systems. So let's look at the different tankless and how they would compare. So we have 60,000 BTU delivery on the heating side. The minimum input, 20,000 BTUs for the NP240A or 240S, gives us a 33% turn down ratio, or 3-to-1. We're looking at the 180A, again 60,000 BTUs, but now a lower input on the 180. 15,000 BTUs are minimum input for a 25% turn down, or 4-to-1. So now our ratios are going way up. We're now 4-to-1 on our turn down. But now let's look at the NHB 55. So this is a 55,000 BTU boiler. Very, very close to the 60,000. It's not exactly matched, but very, very close. Minimum input 8,000 BTUs. So down to 14.5% of our maximum, which gives us a nice turn down ratio of 7:1. On our combi boiler, we have a 60,000 BTU delivery capacity, minimum input 12,000 BTUs, 20% of our maximum, for a turn down of 5:1. And then we've got two new units. Navien will have two new units in March 2021 coming out, the A2 and the S2. 15:1 turn down ratios on those two units, so we're looking forward to using those on the heating side. The NP240 A2 will come in at 13,300 as its minimum input, 33%, or a 4.5:1 turn down ratio. And then the NP180 A2, again 15:1 turn down. It's going to come in at a minimum input of 10,000 BTUs compared to our 60,000 BTU heating input. It's a 16.7% minimum, 6:1 turn down ratio. So again, all of these ratios, if I compare 6:1, 4.5:1, 5:1, 6.9:1, all much better than the heating side. So again, the lower the input, right, the lower the minimum input, the less cycling there will be, the better efficiency there will be. The higher the turn down ratio, same thing, the higher the turn down ratio, the less cycling, the better efficiency will be. And again, the turn down ratio is just the maximum input divided by the minimum input. And it gives you an idea of what the range of operation is. So, what does this all mean? Well, what it does mean is that the 60,000 BTU furnaces are most often supplying more heat than we actually need in the home. For an example, if it's early October, and it's a night in October in, let's say, the Northeast, and we need 15,000 BTUs worth of heating. If we go back to our two-stage furnace, even the two-stage with the stage 1 at 50%, right? We've got 60,000 BTU furnace. It can only deliver at 30,000 BTUs as is minimum, right? So we're going to use that furnace as an example. So we're bringing that 60,000 two-stage furnace, delivering 30,000 BTUs, but I only need 15. So it's delivering twice as much heat as I need, actually, right? So if it's providing twice the amount of heat that I need 15,000 BTUs, it's able to give me 30 at minimum. So it's twice the amount. It means that I'll have no choice but to run half of the time. So I run 30 minutes of every hour. Now, do I run for 30 minutes full on and then off for 30 minutes? Or do I run for 10 minutes on, 10 minutes off, 10 minutes on, 10 minutes off, and I do that 3 times, three on and off cycles an hour? That's the way it's most likely going to run. Your thermostat probably wouldn't go for 30 minutes. You'd overheat the space fairly significantly, and then you would really, when you turn it off for 30 minutes, then it would really drop. So all it means is, now we're talking about how the equipment will function, but now we're going to relate it to comfort. When you have those, you're having extra, relatively speaking, larger swings from set point because you're on for 10 minutes delivering more heat than needed, and then you're off and the temperature's dropping because it's, the furnace is completely off. So in terms of comfort, it's you're going to be overheating for 10, no heating for 10, overheating for 10, no heating for 10 is kind of the way it is. So you're going to have those larger swings. Ideally, you see this red line, if we can deliver only the BTUs that are needed, so if we in this case 15,000 BTUs, if I have an equipment that's going to be able to modulate down to 15,000 BTUs, it'll be perfect. I'll be able to bring it on. It's going to run for the entire hour at 15,000 BTUs, so it's not going to turn off. So you may say, well, it's running so much longer. It's running for the hour. Well, it's running longer, but it's running at a lower level, lower CFM rate, lower inputs, running at 15,000, not 30,000, and delivering constant comfort. It's like setting the cruise control in your car. Okay, if I only need to go 15 miles an hour, I can set the cruise control for 15 miles an hour, and it's just going to go and purr along. It's going to still run, right? It's going to run continuously, but it's going to run nice and smooth at that nice and efficient level, because it's not going to be cycling. So again, looking at the furnace again, we have our heat load. We know where we don't need to, where no heating, and we have our maximum. And then if we have that 30,000 BTU furnace, again, just pictorially, what it means is we are not going to be able to deliver in this area, right? The 15,000 BTUs was kind of in this range, is where we would need it. We'll be cycling on and off because the furnace can't modulate down in this area where we need it to. So, recent studies. There have been 2 independent, unfunded by iFLOW. We didn't support it, we didn't pay for it. It is completely independent, arm's length, third-party studies that looked at forced air heating performance at various part loads. So the first study evaluated 8 condensing furnaces at the 60,000 BTU range. And again, because that's the most commonly used furnace size in North America. 4 of the 8 furnaces were modulating condensing furnaces, so very high end. 3 were single stage condensing, and 1 was a 2-stage condensing, but tested at stage 1, that lower minimum input, because we're testing to part load, so we want to make sure we're testing its efficiency at the lower end. The average AFUE of those 8 furnaces was 96.2. So again, these aren't low efficiency units. They are all very high efficiency units. And then the second study evaluated the performance of an iFLOW hydronic furnace with a Navian NP tankless water heater to that same part load distribution. So first study measured the 8 furnaces to the part load to see what the performance is. Not only what the AFUE says, but at part load, where it's actually on and off and trying to deal with those lower part loads. And then we evaluated a combi system to that same heating distribution. And let's see the results. So, result number 1. None of the 8 condensing furnaces outperformed the Navian combi system. Right? None of them. The iFLOW combi system outperformed the average of the 8 condensing furnaces by 9%. So again, none of the furnaces outperformed the iFLOW Navian combination system. And when we averaged all of the furnaces, because we don't know which one we're going to be up against, are we going to be up against the best performing condensing furnace or the worst performing? Well, we don't know. Are we going to be up against a modulating furnace or a single stage or 2? We don't know, so we just averaged them all, and we outperformed that average curve by 9%. Noteworthy, 7 of those 8 furnaces are Energy Star program furnaces. So we're not testing against the worst of the bunch, we're testing against the best of the bunch. And let's see how we did. So pictorially, these are the results. So the red line is the Navian iFLOW curve, and the dark gray line is the performance of the 8 furnaces all averaged together. And you see that as the furnaces, so what we have on the x-axis, we have the BTUs needed, right? Or the percentage of operation based on the 60,000 BTUs, so total 100% load. So you see that we started very low inputs, right? 3,000, 6,000, 8,000, 9,000 BTUs, right up to 60,000 BTUs. But we've plotted our efficiency curves against the distribution curve that we talked about earlier. And we have the 2 dotted lines that represent the majority of the operation or the majority of the demand in our, let's say, our model 1,600 square foot home. And again, if it's a larger home, it'll shift a little to the left, or a smaller home, little to the right, warmer area, little to the right, colder area, a little bit to the left, but nonetheless, very, very, this is the average, very representative in our opinion. So, as we increase the BTUs, what happens? The efficiency gets better. Well, this makes sense because we're not going to be cycling as much. As you need more and more heat, closer to that peak in January that we looked at, the furnace is going to be running more, it's not going to be cycling as much, and as a result, the efficiencies go up. Not unsurprising. That's exactly what we would expect. However, when we go the other way, when we're using less and less heat in the season, we see that the efficiency starts to drop. Why? Again, not magic, because it has to cycle more. If the minimum inputs aren't able to aren't low enough to be able to modulate down to those levels, it's going to have to cycle on and off. Every time it cycles on and off, it has to post-purge the heat, expel the heat that is built up in the heat exchanger, cool it down, and then when it fires on again, it has to heat the heat exchanger up, then pass the air across it and deliver it into the home. So every time it has to shut down and then start up again, shut down and start up again. And if it's cycling on and off, it's losing efficiency. That efficiency isn't calculated in AFUE, and we'll talk about that. But all to say, if it's cycling more, it's going to lose efficiency. And that's why you can say, well, we have great efficiencies with a 96% AFUE, but we see that it's operating in the area where you need the actual demand. It's operating for most of that in the 80% range, nowhere near 96, unfortunately, because of the cycling effect. Whereas with the Navien iFLOW, or the iFLOW Navien combination, we're able to modulate lower than the furnaces were, and I showed you the results. I showed you those lower inputs, and this is the effect of that. When we can modulate down to lower inputs, we are not going to be cycling as much at those lower levels, and we're able to ride this curve much, much better. So as the heating demand goes down, we're able to run the burner down and continue to deliver without cycling on and off. And that's the advantage of modulation. That's the reason why we got the 9% advantage. So as we again modulate down to these lower inputs, the advantage of the iFLOW Navien combination was 12.5% better on the lower end of this distribution, and 5.5% on the higher end. So as you cycle less, the efficiency comes up, no question. But as you cycle more, the efficiency goes down, for an average of 9%. So that's where we got the 9% increase of efficiency increase of the iFLOW Navien combination system over the furnace system. In terms of the industry and looking at it, this gold line in the bottom represents an 80% single stage non-condensing furnace with an ECM motor. And then we step up into the average condensing furnace. So you see there's a significant increase from the single stage non-condensing up to the condensing, which is great for the industry. The iFLOW Navien combination system now takes even that condensing furnace line and jumps it up another level. So it kind of a momentum shift, if you will, in the efficiency performance of your HVAC equipment, right? Offering you kind of a better solution. Why? Because we're able to modulate better at the lower end. So again, it's not magic. Let's look at AFUE. So I get this comment often, okay, the furnaces I use are Energy Star rated, they're 96% AFUE, Energy Star rated. How much better can your system be? How much more efficient can it be? Well, we saw by this graph, it can be much more efficient actually, because it's able to modulate in the ranges where most of your heat demand is. Don't be misled by AFUE. AFUE is like quoting your car's MPG highway when almost all of your heating is going to be done at MPG City. So AFUE should be requiring a an MPG city, or, a city rating, but it doesn't. That's not part of the test, unfortunately. So when the unit is operating, right? When I'm testing the unit at maximum, which is part of the AFUE, then not a problem. I test the furnace, or I bring it on, I run it at that capacity, I test my efficiency. Hey, I'm going to get a good number. Even at minimum, I run it at minimum. Okay, let's operate it. I still test, still running. It's fine for that. Let's say that 10 minutes that it's on versus the 10 minutes that it's off. Okay, I run it and I get a decent number. But it's the cycling that's not taken into effect. So be aware that AFUE does not measure the negative effect of cycling. Right? That heat loss that is post-purged out every time the unit cycles off is not measured in the test. So that's why you're getting very high efficiency numbers, but that aren't relative to what you're actually seeing in the field. That's why manufacturers use numbers like, or qualifiers like, potential for savings, or will reach as high as a certain percentage efficiency. They're never going to say it's always going to operate at that efficiency, because they know it's not going to when it starts to cycle. Unfortunately, the Energy Star program uses AFUE as their main determinant. So saying I've got a high AFUE and I'm on the Energy Star program is like saying the same thing, because once you hit a high AFUE, you're on the Energy Star program, and then many of the rebates are based on the Energy Star program listing. So unfortunately, the whole industry is kind of arranged around AFUE, which is, again, not a great number because it doesn't reflect the real efficiency of your system over the part loads. So that's what this study looked at. In particular, it wanted to see what are the effects of that cycling, and how do the furnaces, how does the equipment operate? So I'm going to give you an example of how AFUE might be misleading. The heat loss, let's see if you agree with me on this. So the heat loss of a 1,600 square foot home does not change based on the equipment that's installed, right? When I calculate my heat loss, it's based on the R value of the walls, the square footage of the windows and the R value of the windows, the doors, the wrap, the insulation in the attic, the floor coverings, all kinds of different numbers go in, but the equipment is not a function of that, right? You calculate the heat loss of the home, and that is what it is, and then you figure out which equipment you're going to use to run it. Am I going to put a boiler in? Am I going to put a furnace in? Am I going to put a combi system in? How am I going to do that? But heat loss is the same. So whether I use a 95% AFUE 60,000 BTU boiler to do radiant, or with an iFLOW to do the space heating, or whether I use a 60,000 or 95% AFUE 60,000 BTU furnace to do the heating, same thing, right? It's the heat loss is the heat loss. The heating curve also doesn't change. We've looked at the heating curve a number of times, right? Again, 0 in the summer and then increases to maximum back down. That doesn't change either, right? The outside temperature is the outside temperature. It doesn't change. So, given that the heat load doesn't change, the outside heating curve doesn't change, whatever heat source we select, it should be able to deliver comfort efficiently at those variable loads, right? Again, through the heating season, this does not change. So it should be able to deliver when we need, 10,000 BTUs, 20,000, 30,000, 40,000 in the fall, and then it should be able to deliver at peak, but then it should also be able to deliver those part loads in the spring as well. So let's look at an example. Based on what we've reviewed thus far, right, talking about modulation, talking about loads, talking about performance, talking about turn-down ratio, which of these products would you guess would operate more efficiently in a home? Right? If you were designing a 1,600 square foot home with a heat loss of 60,000 BTUs, which equipment would you select? I've just picked 3 here that we can evaluate just for comparison. So I took the 2-stage furnace with the minimum stage 1 at 50%, with a minimum input of 30,000 BTUs, turn down ratio of 2 to 1, with an AFUE of 95%. I've also selected the condensing furnace. It's got a maximum input of 60,000 BTUs, a minimum input of 24, for a turn down ratio of 2.5 to 1, with an AFUE of 98.5. And then I've selected a boiler. So for this application, I'm going to put in a 60,000 BTU boiler, and I'm going to pair it with an iFLOW. That boiler has a minimum input of 7,000 BTUs, right? 11% of maximum, for an 8.6 to 1 turn down ratio, with a 95% AFUE. So, equipment has the same AFUE, right? 98, or 95, 95, 98.5, so all very high, highly rated, but the minimum input is very different. 30,000, 24,000, and then 7,000. Which one's going to be the better performer? Which one's going to be the more efficient in your home throughout the season? Not only at maximum, but throughout the season. Well, if we compare the top furnace, the minimum input is 30, compare that to the minimum input of the boiler, 4.3 times higher. If we can compare the Energy Star rated furnace, minimum input's 24, that's still 3.4 times higher than that minimum input. Right? So even though the boiler and the furnaces have the same AFUE rating, there is absolutely no question this boiler is going, the boiler with the iFLOW, doing the same 60,000 BTUs heating, is going to perform much, much better, because in all the seasonal times where you don't need the maximum, or you don't need even 30,000 BTUs, as we looked at in that middle of October example, the boiler is going to operate, if I need 10,000 BTUs, because the minimum is 7,000, it'll just deliver at 10,000 BTUs. iFLOW is going to pick up that heat and deliver it into the house. No problem at all, no cycling, constant operation. Constant operation at that 10,000 BTUs, if that's what I need. Even right down to 7,000 BTUs. That's going to cover you the majority of the heating season, from September right through. Because of that minimized cycling, this system is going to outperform these other two by a minimum of 10%. Why? Because the lower minimum input is delivering much less on-off cycling. And that's really, this is the stuff that's not taken into account by the AFUE rating. So less cycling, better efficiency, better comfort. So even though the AFUEs are the same, very, very different performance in the field, unfortunately. Fortunately for us, unfortunately. So, just a note on AFUE. Avoid the pitfalls of these silos and assuming that AFUE is the number, right? AFUE does not measure the cycling losses. So you as the homeowner, the contractor, the builder, will have to do your homework, unfortunately. So how do you determine what's going to be the best one? What's the best heat source? Well, you got to look at the heat source that's the best at converting the heat to gas, or the gas to heat, sorry. You can consider AFUE as, let's say, the peak efficiency. That's the peak efficiency possible. But then you also have to consider right sizing. So you want to make sure that if your heat loss is 60,000 BTUs, don't put in an 80,000 or 100,000 BTU furnace saying, well, if I put a bigger is better and I'll never run out of heat. No, because the higher the maximum input, the higher the minimum input is. So now you're compromising your efficiency because you're oversizing your system. And now that furnace, when it comes on at maximum, now it's blowing 100,000 BTUs instead of 60. So oversizing is not helping at all. Right sizing is the best, bigger is not better, right? Then once you have the furnace or the heat source sized to your maximum input, then look at the minimum input. What's the minimum turn down? What's the minimum input of that equipment? which is going to be able to turn down better, just like the boiler example we looked at, right? In this case, well, the boiler is going to turn down to 7,000 BTUs. It's going to be much, much better than a 30,000 BTU option or a 24,000 BTU option, right? So, which has the wider modulation range, which has the better turn down ratio. So these are all things that you can look for. Is there outdoor reset capability? So will your furnace or boiler look at the outdoor temperature and automatically compensate up or down, modulate up or down based on the outdoor temperature? That could be another feature that would help. Which one has the lower emissions? Again, we're talking about, climate is such an important part of things we think about today, and we're trying to get the best efficiency. Why? Because we're concerned about emissions. So which one has the better emissions could be another part of our consideration. So just to conclude and wrap up, the iFLOW Combi system, the outperformance is not rocket science, right? This is not something difficult to understand. The ability of the Navion burner to modulate down to relatively low inputs means there's less cycling. Less cycling is improved efficiency, improved comfort. Then iFLOW's unique heat transfer, right? Our hydronic control strategy that we employ inside the iFLOW maximize the efficiency of the air distribution. So the Navion creates the heat, we take the heat, deliver it into the home most efficiently. Pairing of these two advanced technologies into one powerful system delivers the most comprehensive and fully optimized forced air solution in the market available today. And that's what the two studies showed. The iFLOW Combi system, right? The modulation results in longer run times. As I said, we're going to be able to run. If we need to run at 7,000 BTUs, we run at 7,000 BTUs, but we can deliver the 7,000 BTUs efficiently for the whole hour instead of cycling on at 30,000 BTUs, delivering too much, then having to shut down for a period of time where your temperatures are kind of going up like this. We just run at one constant temperature, right? So longer run times, but at lower inputs using less energy, delivering better temperature consistency, quieter operation because we're running at those lower levels, longer life expectancy because we're not cycling the unit on or off, right? We're running continuously. And that is the ideal for ultimate comfort as well. So we're not talking only about efficiency, we're talking about comfort delivery. So, next step. When you're considering your next HVAC project, please consider an iFLOW Navion combination system that's going to deliver endless hot water on the tankless side and a cozy warm home, all from the same combi system. It's going to be the ultimate in comfort and efficiency. So I want to thank you for your time. I appreciate it. If you have any questions, please reach out. My email, my cell phone number are there. We appreciate the time you've spent with us. Hopefully it's cleared up a few things about efficiency, part load heating, AFUE, and kind of identifies what we at iFLOW do a little bit differently. So thank you again for your time. We appreciate it.